Starting a unit on acids and bases, I guess you have to define what is an acid and what is a base. And the only hurdle we run into is the fact that there's more than one definition, and they kind of follow different patterns or different levels of understanding. The most basic definition of what an acid is or what a base is the Arrhenius definition, which states like what I think we would expect. When we associate acids, we expect something with hydrogens, and when we expect bases, we're looking for something with hydroxides. And that's what the Arrhenius definition says. It says that an Arrhenius acid produces those hydrogen ions in solution, right? And an Arrhenius base produces, unsurprisingly, hydroxide ions in solution. And I think that is what most people see as acids and bases. A very, very simple Arrhenius example of an acid might be H plus, right? Sorry, HCl, which is going to dissociate to give you H plus and Cl minus, right? Making H plus. A very simple example of a base might be a strong base like sodium hydroxide. NaOH is going to dissociate to give you sodium ions and hydroxide ions, right? And these are in solution, so they'd be aqueous, 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 aqueous. So there we go, Arrhenius definition for acids and bases. Now, if we move up the hierarchy a little bit, we've got the Bronsted-Lowry definition, which is a proton donor is an acid and a proton acceptor is a base. And that's kind of ambiguous terminology, which is why when you're first learning about acids and bases, you work with the Arrhenius definition. They don't even call it that, I think, because it sounds scary. So our Bronsted-Lowry acid is a proton donor, and a Bronsted-Lowry base is a proton acceptor. And I think out of context that seems a little scary because we're talking about a proton, which is part of the nucleus, and generally the nucleus isn't changing in ordinary chemical reactions. But don't worry, these are ordinary chemical reactions, and the nucleus isn't changing, it's just how we've labeled something. So if we look at protium, a hydrogen 1 isotope, it has 1 proton, it has 0 neutrons, and it has 1 electron, right? If we make this the hydrogen ion, H+, we're going to remove that electron, and we end up with 1 proton, 0 neutrons, and 0 electrons. It is a proton. A hydrogen ion is just a proton. So that's where that comes from. And a few things that I want to note, H+ is a proton. And in solution, in aqueous solution, your H+ and your water make H3O+, the hydronium polyatomic ion. So in my other videos, I'll use H+ and H3O+ interchangeably. In some books, they're really, really insistent on just writing H+. In other books, you'll see H3O+. I tend to lean towards the H3O+, even though I'm super lazy, because that's what we're working with in the water. So I'm going to erase this, a proton, H+. So this is actually quite a bit of overlap here because this produces H+, and this is something that supplies a proton, and this is something that accepts a proton like an OH-. So if we look at an example here, I can take something like HBr, right, and maybe put that in some sodium hydroxide. I'll just do that OH-, and we're going to get, in this particular case, this hydrogen is donated, this hydroxide accepts that hydrogen, and we end up with H2O and Br-. So this is our Bronsted-Lowry base. It accepts that proton. And this is our Bronsted-Lowry acid. It donates that proton. And these are all equilibrium systems. I did cut some corners there. And we should take note that these go in both directions. If you have a strong acid, it's going to dominate in the product side. It'll be product-favored equilibrium. And if you have a weaker acid, at least in an aqueous dissociation, it'll be reactant-favored. All right? And then our last definition of interest is the Lewis acid and base setup. And you may or may not remember from the discussion of structures, molecular structures, Lewis structures were one of the ones that we saw, and that's relevant to how we're going to deal with our Lewis acids and bases. So a Lewis acid is something that is an electron pair acceptor. All right? And a Lewis base is something that has an electron pair donor. And there's a couple other vocabulary terms I want to sneak in. And I do want to mention, this says donor for acid, this says acceptor for base, and this says acceptor for acid and donor for base. And the key distinction there is, here we're talking about protons, something that has a positive charge, and acids are supplying it. And here we're talking about electrons, something with a negative charge, and bases are supplying those pairs of electrons, and the acids are accepting them. And that's what's going to open up our definition to a bigger umbrella. For most purposes, this is going to be good enough, right? In fact, for almost all of first-year chemistry, the Bronsted-Lowry definition is the only one necessary. As you start to look at complex equilibrium systems, then the Lewis acids and bases become a big factor. So let's take care of a couple other vocabulary terms, and then we'll look at an example here, and then we'll look at a scarier example, and that'll be the end. Another name for a Lewis base is a ligand. And depending on how you talk to, or who you talk to, chemists generally call it a ligand, biologists generally call it a ligand, which kind of makes sense, because the verb form is to ligate, or to separate, I guess, to attract or surround. And so a ligand is what we call a complexing agent. And I think that without going into detail on this now, these things surround and separate. That's how it works. And we'll see that with our Lewis acids and bases. So if we take a step back here, Lewis structures, we can see how Lewis acids and bases work, but we have to look at Lewis structures to make that happen. And I'm going to look at a very simple example, and then I'm going to look at one that's not as simple, and we'll be all set. So looking at these, it's no surprise, we can have something like H+. H+ can accept an electron pair, and I could have something like OH-, and I'm going to be more careful about setting this up as a Lewis structure, and we can get H2O. All right? In fact, I want to draw that a little more Lewis setup. I guess we're stuck with that mysterious drumming in the background, but if you look right here, this hydrogen accepted an electron pair from the hydroxide, and then we got this water, H2O. So the key idea there was this electron pair was accepted by this, and then things stuck together. We have our Lewis acid and our Lewis base, and let's identify, I guess this is our Lewis acid and our Lewis base. So this, I think, is fairly straightforward. This, in fact, all of these simple Lewis acids and bases would fit under the Bronsted-Lowry definition. But let's look at something that's a little more complicated and maybe a little less obvious. And I'm going to try and budget my space so that this works out. It turns out that something for Lewis acids that doesn't apply here are things like metal ions. So for instance, you could have something like silver, Ag+, plus maybe the cyanide polyatomic ion, and we'll ignore any Lewis structure controversies there. But if we have a situation like this, we have some electron pairs that could be donated, we have something that can accept an electron pair, and we end up with, in this particular case, silver, for instance, there's many ways you can do this, AgCN2 with a 1- charge. All right? So we do need to put that 2 right here. The silver in this case is our Lewis acid, and the cyanide is our Lewis base. And then we have this system right here. So one of the analogies I use in like water is a Lewis base, and then like sodium ions or chloride ions or whatever, the sodium ions can act as a Lewis acid. And something I've mentioned in other videos and that I mention to my students frequently is that there is no NaCl in an aqueous solution. You have sodium ions and you have chloride ions, and whether or not this is an appropriate way to explain it, it's, I think, reasonable in terms of intuition, which is water is polar. It has a net dipole towards that oxygen, so that's the slightly negative end of that molecule. And what that means with our slight negative and our slight positive is that if you have something like NaCl, we have sodium ions and we have chloride ions, this negative end here can be attracted to that sodium. And then the waters come in and start to push those chlorides away. And this isn't the world's greatest example, and it's not necessarily 100% true or perfect, but the waters come in and surround that sodium ion, they complex it out from that chloride, and so then we've got chloride over here, not by itself though, and that's good news, because there's also a positive end to these waters, this hydrogen end, so HO, H, H, O, H. And I think that when you look at it, I say it's like a rock star effect, which is like if a band were to walk out into the audience together, all the fans would rush in around each member, and then the members get pushed apart. So with these electrolytes, the waters kind of rush in and push things apart. This might have been like an AgCl or something, which is technically insoluble, but when you put it with a complexing agent, you can make a soluble complex ion. So these cyanides would rush in. This has a stronger partial negative dipole. It is more attracted to the silver than the water would be, and that's why it makes it soluble. It can get that chlorine or chloride ion out of the way and then surround it. So anyway, it's this idea of this rock star effect pushing things apart. And I think that analogy is especially helpful when you talk about like how can a solution get saturated. Well, there's a finite number of water molecules in a solution, and if it takes some number of water molecules to surround some ion, eventually you're going to run out of water molecules that can surround things and push them apart. So you run out of available water molecules, and you run out of the ability to dissociate things. So this might be a fairly straightforward example of a Lewis acid, Lewis base situation. Another one that I just want to mention, just because they start to look very scary, and we'll get into more with equilibrium and complex ion dissociations, but you could have something like iron, all right? The iron ion, maybe like the iron ions in your blood, right? And maybe we've got some Lewis base, and I'm going to pick water in this case, but it might be useful to do like carbon monoxide or something. So we'll say we've got water, H2O, and we do want to look at this in a Lewis setting, because that's telling us what our electron pair donor is. We can see him right there, and what our electron pair acceptor is going to be. And so we end up with, and I'm going to change my drawing a little bit here as we see it, we end up with this iron ion, and it's still a 3+, but it's surrounded by waters, all right? And I think that while that matches exactly what I said before, this has a little more meaning, because the formula for NaCl doesn't specify like any waters are required or whatever. But the formula for iron, the iron, 1, 2, 3, 4, hexaaqua iron polyatomic or complex ion is this. It happens to take 6 of these waters, and we end up with Fe, H2O, 6, 3+. The hexaaqua iron 3 complex ion. So this is how that ends up. And the reason I want to mention that is like if you look at oxygen in your blood, iron ions carry that oxygen around because that oxygen is a Lewis base. It has electron pairs to donate. This is a Lewis acid. This is a Lewis base in this case. So these oxygens stick to the iron, and your iron carries them around in your blood. But things like the cyanide polyatomic ion we drew earlier, that's a better Lewis base, and it sticks to the iron better. And then you die, right? So if you've got that CN like this with its 1-, this happens to be better at sticking to the iron and complexing the iron out than the oxygen is. And all of a sudden, oxygen can't stick to that iron. Iron can't carry oxygen around your blood, and you die. And the same thing is true for like carbon monoxide or other things like that are better ligands, better complexing agents than water or oxygen in these cases. So that's the basic idea of what an acid or base is. The Lewis acid, again, is huge in terms of our equilibrium systems, and it's a bigger umbrella because it includes things like these metal ions. But Bronsted-Lowry is good in most cases.